one of the more interesting things is that there is, in cylindrical cells at least, there's a inbuilt um, safety mechanism, right? It's essentially like a safety relief valve almost.
Right. Is that rubber gasket kind of a thing at the top? Right.
So if you push the cell too hard, that'll pop.
Okay.
Right. And it'll release some gas, and then it sometimes goes back and sits, and you can use the cell again. But the activation of this can be wildly different at different conditions, right? Like if you do this test at a certain temperature, at a certain voltage, at a certain current, it will be very different from even you change those conditions, right? So you got to understand these nuances of various cells. Then, of course, depending on the chemistry, and if you're using NMC 622 versus 811 versus NCA, the thermal runaway characteristics vary wildly, right? We found NCA to be particularly explosive, right? Very surprising. We didn't expect that, but when we tested one of them, we were like, wow.
Hello and welcome to Declassified, Ather's community podcast where we talk about the things happening behind the scenes and the journey of Ather. Today we have Shreyas, who leads the battery team at Ather.
Hey, yeah. So I'm Shreyas, like Abhishek said. I look at battery and powertrain primarily at Ather. So my teams work on the battery pack design, the powertrain layout. So that includes the motor, transmission. So we design pretty much everything from scratch.
Considering all of the current scenarios around battery fires and whatnot, suddenly you have been catapulted into the mainstream discussion, right? How do you feel about this?
It's not good for the industry as a whole. There's a trust deficit now. People don't want to park it in the sun. People don't want to park it, in the basement. So definitely a setback for the industry just when it's really taking off, right? That said, I think it's a necessary conversation. We should have it now rather than, a few lakh more units down the road, right? So yeah, good time for maybe the whole industry to pull up its socks and do a better job.
So before we jump into, I think, battery packs and what's been happening, how did you get into this space? Like what interested you in battery packs in the first place? If I'm not wrong, you joined Ather around 2014, 2015 or so?
It's a bit of a story, actually. Not 2015, actually 2017. Okay. It's been 5 years. So I fell for a billboard.
Okay.
I'm glad I fell for it. But Ather used to run a campaign called Save an Engineer. Lots of t-shirts you can see around it, and they very cheekily and sort of why I liked what they did as well is they put a billboard smack in the middle of Whitefield, where you'd be waiting at a signal, getting frustrated about Whitefield, wondering what you're doing in life, right? That's exactly where they put up a billboard saying Save an Engineer, nothing else, right? No logo, nothing. And so obviously you get to office and you're like, okay, who are these guys, right? And essentially it was a hiring campaign, and back then they would ask you a question apart from your obviously submitting your resume. They'd ask you, okay, why do you want to take the red pill, right? And so you had to give an answer, and I wrote a very creative answer, and I applied to the chassis team actually, but then interestingly I got a call for battery, right? So I had no intention of becoming a battery engineer. It's almost serendipity. That's it. And back then you wouldn't find battery engineers. So you generally hire for good mechanical designers, right? And then sort of teach them battery, right? So that's I actually at the same time was considering going abroad for a master's. So when Ather clicked, it was like super confusing, and Ather is in Indiranagar, was sort of the battery team at least was based in Indiranagar. So in true Ather Indiranagar fashion, I went to Toit, had a couple of beers, and then I was drunk enough to make the decision that no, this is the right thing to do, right? So yeah, I mean that's how it started, and from there on, it's when you're building things from scratch, you learn. From there on, it was just okay, put the 450 out in the market, go through that journey, then make improvements to the battery to put it in Chennai and Pune and stuff. One second journey, right? Then the third pit stop was put it on the 450X 21700. through the pandemic, right? Scale it up, and then now we're going through another chapter, right? For the next iteration of the battery, and yeah, so it's almost been 4 generations of batteries now.
Diving right into the big question, why do battery packs catch fire?
Well, a bunch of reasons. Lots of energy, obviously. I mean, it's primarily because we still use liquid electrolytes, which are quite combustible, right? And if you abuse these batteries in primarily 4 different ways, if you overcharge them, if you expose them to too much heat, if you abuse it mechanically, and then if you short circuit it, right? Then what happens is these batteries can go up to a temperature where they then catch fire, right? So it's primarily those 4 reasons. But why does it even catch fire? Is because the contents are flammable. But that's what gives it the energy density that it has, right? So someday in the future, when solid state becomes a reality, solid state batteries, we won't have the same kind of problems. But today we do. And that technology is nowhere close to the kind of scale we need for electrification at the moment. So this problem is here to stay for some time. We got to deal with it, right? And you deal with it with good design and some smart engineering.
Okay, interesting that you talked about good design and smart engineering, because what we have heard, at least so far, is not is okay. Only the battery packs in vehicles when they catch fire seems to be coming to the mainstream, right? There are fixed energy solutions. There are other solutions as well. But when you got into making the battery pack for Ather, what were the considerations? Like, what makes Ather's battery pack different?
Well, I mean, literally the first consideration, and I'm not saying this because we're putting this podcast out. Literally, the first consideration is always if I lose one cell, right? If one cell is going to go up in flames, will the rest of the pack go up in flames, right? So from the very beginning, our philosophy sort of been, yes, we want to push the envelope on performance. Yes, we want to fast charge as much as we can. But all that said and done, if we get a bad apple of a cell, right, and that internally short circuits and goes up in flames, it should not propagate, right? So I think that's sort of what set us apart. And back in the day, when the regulations hadn't really caught up, when AIS 048 was sort of the norm. Now we're moving on to a new standard, but when that was a norm, that actually had this really weird test where you had to stick a nail through the battery pack, and it still shouldn't catch fire, which is frankly a very, very stringent requirement, almost impractical for lithium-ion batteries, and which is why it's being done away with now, and the regulations have changed. But what we took that seriously. We were like, you know what? Let's stick a nail through this battery and still not have it go up in flames. So there was all of this engineering when that standard was in place to somehow make the battery pack not go up in flames despite that, right? And we were fairly successful, surprisingly. So we kind of tweaked the spacing between the cells. We put in special materials inside, and we're at the point where we could actually do it, right? We could stick a 100 nail through this battery pack, and it would not completely catch fire.
Okay, so for example, let's say I have a fixed storage solution. Would that have to undergo the same level
the
of
standards
test?
for that are different. And even for EVs, right? The nail penetration test doesn't make sense, and that's why it's been done away with. But that said, EVs will crash. EVs will undergo mechanical abuse. So you still need to design it for a reasonable level of abuse. So when we moved away from that nail penetration test to a more realistic sort of test scenario, what we realized is we swung to the other end. It's too lenient, right? And while that has been good because more people can enter the space, for us it was like, wait, like we always start from we start from this. How can we not have this test anymore? So then we started developing our own sort of standard, right? We were like, okay, you know what? Yes, nail penetration was super duper hard, but this is still very important. So we have our own test and we evolved our own test procedure to ensure to kind of simulate an internal short situation.
Is it possible like a small rock or a nail or a chip or something goes into the battery pack?
That can happen, right? But then a nail to go 100 through it's almost like very improbable sort of use case, right? What is a more probable use case, and which is what is probably happening in all of these cases, is you have a defective cell, or you overcharge the cell, you abused it electrically, and then that goes up in flames, right? And that can happen in the middle of the battery pack, right? So you've got a test for that, right? Unfortunately, the standards don't call that out today, right? But in our opinion, it should, right? You have to be able to survive that kind of an event, because we're putting. Today the 450X has about 168 cells in it, right? And if you're talking about a scale of 100,000, 200,000 vehicles, you can imagine the number of cells that are out there, right? And the expectation that every cell will be perfect is sort of, while yes, cell quality today is so good that if you get the best cells, it's only like a 1 in 10 million chance that you're going to get a bad apple. But 10 million is actually a number we're going to, right? In terms of the number of cells. So you've got to bake in that possibility in your design, right? So that's sort of what sets us apart. We have we're very careful about the cells we use. We're very careful about thermal runaway. We're very careful about short circuit. We have multiple layers of protection. We're very careful about redundancy, right? Anything that's safety critical needs multiple layers of redundancy. So that's sort of what sets us apart.
So I think the point about cell quality is pretty interesting, right? And we've heard conversations about different grades of cells being out there as well. The parallel that I could find was in the processor or the microchip world, where you're basically growing silicon on top of silicon wafers, right? And depending on how it turns out, the chips are marked as different things. So a really perfect chip could become like an i9 processor, whereas a chip with some defects would become like an i5 or an i3 or something. Is that how it's also in cells? Like, how do you go about picking the right type of cells?
You don't actually drop performance, levels like that. What does happen is there are minor variations in voltage and capacity, which is obvious because you're essentially putting a bunch of chemicals and stuffing them in a can, right? So you're going to have variations in voltage a little bit in millivolts, right? You're also going to have some variation in terms of the capacity itself, just the amount of material there is. So cells do get binned according to that, right? So when you get cells from your supplier, they'll tell you that, this is a certain grade and this is a certain grade. And it's actually important to try to sort them according to that, because if you have like a very large voltage variation between two cells that you use in the pack, then it's a little more of an effort to balance it, right? And if your BMS isn't good enough, there's a good chance you will end up overcharging one of these cells, right? So that's one of the fundamental sort of quality checks that we do, right? When cells come in, we make sure we bin them, and then it's kind of picked up by the robot, put in the pack, and so on, right? It's also important to double check this. So before the while the robot is picking it up and placing it, we also do check the voltage and the impedance of the cell. So we know what's gone inside a pack. We know exactly the values of voltage and impedance. All this is actually should be fairly standard, and we've always believed it's standard process. But when these incidents happen, it kind of makes you think that maybe not everyone's doing it, right? And you should be doing it. These basic sanity checks need to be there.
Can we talk a little bit more about the choice of the packaging? Because normally, in a laptop or a phone or something else, right, you don't get to see the way that it's a single cell battery. So the way it's packaged is usually like a plastic or some I think paper is what it feels like, right? But we use a aluminum battery pack, and that's very proudly displayed in all of the experience centers as well. So how did that choice of the packaging come about, and why is that important?
I think very early on, maybe it's because it was a young team, and we were all very performance obsessed at Ather, right? So it wasn't enough for us to say we'll do 80 kilometers an hour, right, or 90 kilometers an hour, right? It was important for us to do that, for a consistent period of time, right? Because otherwise, you're getting this little joyride and that's it, right? So consistency as a concept in EVs is not brought up as much, but I think the consumer is smart, right? They're beginning to appreciate that. So because we were performance obsessed, we wanted to go as high as possible, as far as it's safely possible, right? And we wanted to sustain that. So for us, it was always like okay, if we had to put a thumb rule on it, it was something like at 45 degrees, right, of temperature, ambient temperature. So our goal was, okay, we should be able to do 60 kilometers per hour for half an hour, right? Before you get to a temperature where it's not safe anymore, right? Or it's not recommended anymore. It was sort of like our internal goal to do that. And so we were designing for that. And then when we put it out, we realized nobody's even pushing it close to that, right? So I think it starts from there, this consistency story. But now I've lost track of what you actually asked.
No, so the packaging of the
packaging. Yeah,
why do we use aluminum?
So yeah, I mean, once you say performance, I want this high performance. I want consistency. You can't have plastic, right? Like, you need to dissipate that heat. It's a decent amount of heat that gets put out, and the people might say it's a battery, it's barely generating a few hundred watts of heat, but the challenge with batteries is you're doing that in a very tight temperature band. So you can't go above 55 degrees, right? And your ambient is 45 degrees. So you've got 10 degrees to play with, right? So how do you design for that, right? How do you get half an hour at 60 kmph, 45 degrees with that kind of band? So, I mean, this is no secret. We've spoken about this in Vantage sessions before. We went for a phase change material sort of solution, right? So the thing with phase change materials is it puts the brakes on the temperature, but what it's doing is, while it's putting brakes on the temperature rise, it's also absorbing heat. So you got to get rid of it, right? And there's no way you can put phase change materials in a plastic thing, because then what you're doing is just storing the heat inside the battery. It's not what you want, right? You want to dissipate it. So aluminum was sort of always the obvious choice. The other thing was, our pack is also kind of integrated with our chassis quite closely, right? It adds a decent amount of stiffness to the chassis. And obviously you can't stick plastic in there, right? It doesn't help. Third things began to appreciate, apart from the thermals and the fact that it gives structural rigidity to the chassis, we actually had, during development, unfortunately, a crash, right? And when you see how well the aluminum sort of dealt with it, if you look at the pack, it's also really well shielded, right? It's behind the headstock, the side channels on the side, the chassis on the side. It's also shielded from the rear, right? So it's almost protected from all sides except the bottom, right? We realized that, metallic casings just have such a high safety upside, apart from a thermal upside, and it's part of the chassis, that it just seemed like a no-brainer at that point, right? And I think that with the consistency story becoming more important, you will see a lot more people move to this. The temptation to cut cost and cut weight is always there, but I guess at Ather, everyone's kind of performance wired, so we naturally gravitated to this.
Cool. Let's talk a little bit about how the cells go into the battery pack. You mentioned some 140, 150s, 168 cells, right? How are they placed? Like series, parallel?
Oh, I mean,
does that matter?
Not really. I mean, your voltage level matters. I mean, if you're talking safety, the higher voltage you go, the more sort of protections you need to put in. 60 volts is sort of considered high voltage, right? Beyond that, regulations also get stricter. And obviously, you can you can get hurt or die, right? Beyond a certain voltage level. So we are in what's normally called a 48 volt regime, and so that like each lithium ion cell is 3.6 3.7 volts nominal. So you get you need like about 14 in series, and we have 12 in parallel. But none of that really sort of like, it doesn't really affect safety, right? How far you space those cells does affect, right? So there's always this temptation. I spoke about the temptation of cutting cost, putting in plastic, right? But that's not going to help you thermally. It's not going to help you, from a rigidity standpoint. Similarly, there's this temptation to space cells together as tightly as possible. And yes, you do get more energy density. You can squeeze more range, but you got to always balance that with, okay, what's going to happen if one of these cells go up, right? Like I said, we always start with that question. So the question is, okay, if I put this cell and I space it, only 1 mm apart, how is that going to pan out in a thermal runaway scenario? That's the first question we ask ourselves. So we've always resisted that temptation. We've kept enough so that we clear that internal standard of ours we spoke about, right? Where we set off one cell inside the battery pack, and we expect the battery pack not to go up in flames. So spacing in that sense is super important. That's one of the best levers that you have, really. Apart from the cell chemistry, the thermal design, all of that stuff, if you just want to brute force it, just space your cells out a lot.
Right. Cool. Getting to I think one of the buzzwords that has been going around, which is a BMS, which is battery management system. So what is a BMS? What role does it play in a battery pack? And then how important is it from a safety perspective?
Right. So with great energy comes great responsibility, right? And the BMS shoulders that responsibility. So primarily monitors temperature, current, voltage. Our BMS also looks at humidity. So that's a sort of like an additional feature
within the pack.
Yeah. Okay. Even though it's IP67, it's sealed, we keep tabs on it.
Okay.
Right. Just in case.
Mm-hmm.
Right? So like I said, temperature, voltage, current, humidity. It's also responsible for balancing, which is ensuring that all the cells are more or less at the same voltage. That has actually a huge bearing on safety, because if you got one cell that's, say, 0.3 volts higher than the other cell, so what ends up happening is if you will keep pushing current, through the pack,
mm-hmm.
and all the other cells are charging, while this one has, because 0.3 volts higher, is getting overcharged.
Right. Mm-hmm.
So the BMS is ensuring none of this stuff happens. Right. It's actively balancing, the cells so that the voltages remain the same. It's also responsible for detecting a short circuit scenario. Right. So there is a circuit on the BMS that within a few microseconds can detect if there is a short circuit, and then it ensures that the pack is switched off. Right. We actually get a lot of complaints from people who try to mess around with our battery pack that the short circuit protection acts too quickly, right? And then it shuts down, and then they don't know what to do with it. So then we have to go and fix it. This happened in with some people who wanted to put our packs for solar applications, right? So it can be really annoying, but we're like, yes, it works. Right? So that's in a nutshell what the BMS does. If it's protecting you for overcharge, for overcurrent, for over voltage, under voltage, for too much temperature, too much humidity. If it sees a short circuit, it's keeping tabs on all this.
So we started developing our own BMS from the start, or did we consider other vendors? Are there options available that we could just buy off?
To be honest, I think the decision to build a BMS on our own preceded my time in the company. But we've always wanted to build these things from scratch. Anything that is critical, from a technology perspective, we've always wanted to have control over it. it helps us iterate faster, helps us put more features in. It's hard to find a BMS with the number of features that we have put in the market for the same price, right? So I think that's one of the main reasons we did BMS on our own. I think we've had several. I think there are even more generations of BMSs than there are of the battery.
Wow. Okay.
It's gone through way more iteration than the battery pack itself.
All right. So let's say in a really unfortunate scenario, in the battery pack, one of the cells catches fire or goes into a thermal scenario, right? What happens next? So what goes on in the battery pack?
Yeah, good question. It's sort of incredible actually, because the moment you have a thermal event, what's happening is your cell is short circuited, right? So your positive and negative are no longer separated. They're sort of there's no barrier between them anymore, and at that point you're generating intense amounts of heat. So the what a lot of people don't know is actually the cell is a pressure vessel. It's when you charge it up, the pressure actually goes up. There is gas formation, right? So when something like this happens, the first thing that happens is the cell usually vents. Ideally, you want it to vent if it's a cylindrical cell from the top, right? And so you have these gases that come out, and you've got to get these gases out of the battery pack, because if those gases remain there, it's really hot. You're talking about greater than 800 degrees sort of temperature, right? You want to get it out, because otherwise it's going to heat up everything inside the pack, right? So we've got these vents. Anybody who removes the baffle at the bottom of the 450 and takes a look, you'll find a couple of vents. So first thing that happens in a short circuit is, yes, it starts venting. These gases then make their way out through the vents, right? Now, the other thing, there's three types of transmission ways in which heat can be transmitted, right? You've got conduction, convection, radiation. In a thermal event like this, it's primarily conduction and convection you're worried about. So we try to prevent the heat transfer because of convection by venting the gases out, but that still leaves out conduction, and that's where the spacing comes in, right? The more the spacing between cells, the harder it is for the heat to propagate, right? But then obviously you lose range when you do that. So then if you put materials in between the cell that sort of put the brakes on this conduction, right? Then that sort of helps with preventing the propagation. So if there is no barrier, or there is nothing absorbing that heat, right? Then what you have is essentially thermal propagation, right? So the cell next to this cell goes up in flames, and the next one, the next one, the next one, right? That's what you call runaway. There's thermal runaway at the cell level, where there's an internal short and it goes up in flames. But for the pack, propagation happens this way, right? And that's why when you see a video, you will see first there'll be one
white fumes, yeah,
one full jadi, and then people go near it, and second one, and then third one, and then fourth one. That's the propagation happening. Right. And beyond a certain point, all of them are super hot that they all go up in flames, right? So it's super important to try to stop that, and that's what we've done.
Okay, cool. So you've told us a lot of scary things about what happens in a battery pack. What do we do in terms of testing it to ensure that doesn't happen? So what are the kind of tests that the battery pack goes through from the start to the end?
Yeah, so whole bunch actually. Our test plan is something like 150 to 200 tests. So we test at different levels. We test at a component level, we test at a subsystem level, and then also at a vehicle level, right? All of this is important. You have safety scenarios in all of these cases. So at a component level, specifically to safety, we normally test pushing the cell's limits, right? This is one thing that people tend to ignore. They think, I've got this cell, it's going to behave like any other cell that I've used before. So I'm going to use the same parameters that I used before in terms of my temperature limits and my voltage limits. Uh, even though they might look the same from the outside, the design can vary quite a lot on the inside.
And this is between suppliers, different grades?
Between different suppliers.
Okay.
Even with the same supplier, you can have two cells that behave completely differently, right? Depending on the chemistry, the design of the tab, and so on, right? So really, the first thing we do is push these cells to their limits in terms of the maximum C rate, the maximum voltage it can take. How does the life degradation occur for various sort of conditions? And in the lab here, if you've been there, you'll see there's like an army of cell cyclers essentially that's doing this to collect
charging,
more and
discharging
more
data.
ones. So we thoroughly evaluate the cell, and then we set the limits for voltage and current and all that based on that. One of the more interesting things is that there is, in cylindrical cells at least, there's a inbuilt safety mechanism, right? It's essentially like a safety relief valve almost.
Right. Is that rubber gasket kind of a thing at the top? Right?
So if you push the cell too hard, that'll pop, right? And it'll release some gas, and then it sometimes goes back and sits, and you can use the cell again. But the activation of this can be wildly different at different conditions, right? Like if you do this test at a certain temperature, at a certain voltage, at a certain current, it will be very different from when you change those conditions, right? So you got to understand these nuances of various cells. Then, of course, depending on the chemistry, and if you're using NMC 622 versus 811 versus NCA, the thermal runaway characteristics vary wildly, right? We found NCA to be particularly explosive, right? Very surprising. We didn't expect that, but when we tested one of them, we were like, wow, like, we'll stick with what we have. Thank you. Right? Then there's other subtle things like the cell can, right? How thick or thin is it? Because if it's too thin, if you have a thermal runaway scenario, there's a good chance that instead of the gases kind of venting from the top, the can just gives way, it just bursts, right? And then you have a really bad scenario wherein your gases are venting from the side and directly onto the next cell, right? So you've got to understand these nuances about cells and not take them lightly. So there's a whole bunch of component level cell tests that happen. Similarly, there's a whole bunch of component level BMS tests that happen in isolation. Similarly, for pretty much every tiny component in the battery pack, we have a test plan, right? Then, of course, you got to test it when you put it all together. So generally, we do abuse testing for mechanical abuse, for electrical abuse, put it through a whole bunch of shock, vibration, thermal cycling.
Sprayed with salt water.
Dip it in water. And we don't just do these tests individually. We also mix and match these tests. So we combine abuse cases, right? So most standards call out individual abuse cases and they say, you should pass it. What we do is we start mixing and matching.
So right? Salt water first, and then you shake
then
it.
Thermal, and then vibration, and then so that then gives us a good sense of the reliability of the pack, right? And then what we do is, based on the failures, the testing team actually arrives at a probabilistic reliability number, right? Based on how the tests went. The other thing, of course, is that tests happen so that things go wrong during testing and not on the field. So the other thing is, as we do tests on more and more prototypes, which are at higher and higher levels of maturity, we unearth more and more bugs, right? So initially we get a lot of bugs, and then you sort of work your way through reducing the number of bugs. And eventually what goes into production is bug-free, right? And then finally, of course, there's vehicle level tests. There it's less about safety and more about integration, that it's got to work properly. What happens if for instance, the grounding on some of the components is lost or something, right? Like, does the battery pick it up and shut down, stuff like that.
Amazing. So we'll get to. So we've talked about like manufacturing, testing, designing the battery packs, and more, right? All of that is theoretical. I don't think it's mostly confined in a lab, right? But when you get to the real world, we've had thousands of scooters on road across like multiple cities, including like Jaipur and Vellore and all of that. And we've had a few generations of scooters now come in, right? What is the data telling you? Like how are you able to use that data to make the packs better? What is the data telling you? Are there any things we can do there?
Data basically told us that we went over the top when we first designed it. Probably over designed it, which is fine. I think we were overtly concerned about how people would use it and so on. What we realized is that thermally, we're probably, uh, way better than we need to be. Uh, we also designed for really aggressive fast charge use cases. We realized people don't fast charge as much, right? Um, we we also sort of realized that uh, I actually thought there'd be a lot more crashes, right? And I have a lot more battery packs coming back after crashes saying they got to be replaced. Surprisingly, you know, the and I say surprisingly, even though it is intended, I expect crashes to be a lot worse. Surprisingly, even during crashes, we've not had battery packs,
Damage.
damaged. Is surprising, very surprising. Um, but yeah, those are some of the things that come to mind when when.
But any interesting things we noted when say we started selling in Jaipur now?
To be honest, I haven't looked at the data. Our proxy for Jaipur is Vellore, and obviously we test these things at in the lab condition, so we know what the temperature does. What the user does is more interesting. So there's clearly a difference between a user in Hyderabad and a user in Bangalore. I mean, they have long stretches. It's a bigger city. I mean, in terms of just distances, right? So obviously the performance requirements are a little higher there.
Higher.
So those kind of insights we're getting. But honestly, I haven't looked at a more pan-India sort of data set yet. But we're constantly sort of looking for anything that might be off. That's a constant sort of activity that happens. But yeah, I've also been surprised by how the aging has been. We keep the beginning of every year we say, okay, this is the year when battery packs are going to start coming back. We need to start giving replacements. And it doesn't happen that year, right? Next year, I'm fairly sure it will start happening for our first customers, right? But that's surprised me a lot. Like just how slow the aging has been. Maybe because our first customers are from Bangalore, and Bangalore is sort of a nice, mild climate city for batteries. But it'll be interesting to see how well our batteries do in a Jaipur and all that.
Cool. Okay. So we've now tried to select the best cells. We have checked each of them. We've designed like a great enclosure and tested the battery pack against saltwater vibrations and whatnot, right? Ours is also a connected scooter. So we keep getting data back about the battery pack itself and how it's performing. So what are some of the things that you have noticed so far? Maybe we have some insights about, say, how they've been doing in crashes, how they're doing in different temperature conditions. I think some of our earliest 450 owners have completed more than 3 years. So how is that? What is that data telling you?
Mostly good things, right? It's telling me that the aging isn't as much as we thought it would be. Every year we keep saying, "Oh, this is the year some batteries are going to start coming back." When I say every year, it's literally this year. Sorry. But this year we were very sure it's going to come back, but it didn't, right? We're still hovering in the high 80s as far as SOH goes, state of health goes, even for our most early customers. So that's been a good surprise. The other thing is we probably over-engineered the thermals to the point I don't think people push it that hard. Like our test riders push it that hard, but people don't push it that hard in terms of just sheer battery thermals, right? Probably because they don't get the kind of stretches even necessary to do that kind of stuff. Third, been positively surprised by the fact that even during crashes, uh, batteries have been more or less unscathed, right? Yes, that is part of the intent, but even then, I I do expect crashes to get nasty and for some of the batteries to be replaced, but that hasn't happened, surprisingly. And of course, there are videos of people dipping the 450 in a lake and riding it around. Uh, Not surprised at all that no water went in, right? But very surprised about user behavior in general. Like, why would you do that? But yes.
Cool. So while we figure out why customers do those things, I think there are a lot of people out there who are still trying to figure out like how do they even evaluate EVs, right? I think ICE vehicles have come to a point where we are comfortable with a couple of hundred explosions happening under the seat, right? But there's some nervousness about battery packs. So if you were a customer who was trying to evaluate different vehicles based on available information, like what any advice for those guys?
I think, yeah, you're asking mostly from a battery standpoint.
Yeah.
Okay. Yeah, I think some of the things you have to ask is this thing cooled properly? Look at the track record as well, right? How many of these are out there? Has it been performing consistently? Are there reports of too many battery replacements? Because it's the single biggest cost for a customer as far as an EV goes. So if it's if the promise is a certain number of years, it should deliver to that promise as far as the life goes, right? So I think in some sense, then it's you need enough of these of a certain product on the road for you to be able to gauge that, right? So yeah, I think look at the pack. Is it cooled properly? Is it shielded properly? Look at the track record. Do some research on Twitter. See if there's any complaints about the battery. I think that's what a consumer can really do, right? There's not a lot else. Also, I think quiz the person in the experience center / showroom, right? Do they really know what they're talking about? Also, how much? A lot of these incidents also happen during charging, right? It's good for a company to have its own sort of charger going with the scooter. The reason being, it's important for chargers to talk to the battery, right? So that's another sort of check that I'd put in there.
Great. I think it's been a really fun chat. We've got a lot of inputs on how safe battery packs can be made, as well as the different things that we do. Any things to close it off? What are you looking forward to in the next year in batteries?
I think it's a challenging year as far as batteries go. For the longest time, you had prices coming down. Now there's a lithium supply crunch, right? It's super exciting to be sort of part of an industry where nothing is the norm, right? You think something is the norm and it's shifted, right? So I think what looking forward to is figuring out uh, what's potentially going to be the norm going forward. So that means exploring multiple things and being ready with a solution for whatever will emerge as the dominant technology going forward. Our sort of focus has always been on faster charging, obviously better range, even better reliability, uh, thermal consistency. Right? It's my dream to put a liquid cooling system on a scooter. Right? Finding the space is a different deal altogether, but that would be the holy grail of consistency. Right? Then you can match ICN. So this kind of stuff I'm looking forward to working. Our holy grail has always been 5-minute charging. We want to take baby steps towards that goal. Yeah, so that's what I'd say.
It's amazing that we got through this entire podcast without talking about solid state batteries, aluminum air batteries, and whatnot. But we'll save that for another day.
No, yeah. I mean, I think I'm too much of a pragmatist, right? Yes, these are exciting technologies. Solid state is very exciting. I wouldn't talk too much about aluminum air. The thing is, what people don't realize is cell development is like drug development. There's actually a beautiful infographic somewhere on the internet that compares the two. The timelines are very similar, right? And the process is also sort of similar. So it takes time for something to get to the kind of scale you need, in commercial production. So yes, some of these technologies will evolve, but it's going to take a few years, like 5 to 6 years. Solid state's probably closer than we'd imagine, right? So let's see. Let's wait for something to hit commercial scale, and then we can take it seriously.
Cool. That's it for today. Thanks for all the amazing insights, and hope we have great battery packs coming forward.
That's my job.